Welcome to the lecture of Quadratic Programming Problem. Quadratic Programming Problem is a special class of nonlinear optimization problem in which the objective function is quadratic and all the constraints are linear. So, general mathematical formulation of QPP is minimum f of x. It can be maximum also. F of x equal to x transpose qx plus c transpose x subject to ax less than or equal to b, x greater than or equal to 0, where q equal to qij, that is a symmetric positive semi-definite matrix. Q is a symmetric positive semi-definite matrix. Cx are element of Rn and B an element of Rm, and A equal to Aij is a matrix. So minimum f of x equal to, this is an example for a quadratic programming problem. Here it is not linear, so here we are having power. Minimum f of x equal to 3x1 square plus 4x2 square plus 2x1 x2 minus 2x1 minus 3x2 subject to, these are the constraints, these two, 3x1 plus 2x2 less than or equal to 6, x1 plus x2 less than or equal to 2, and x1 x2 is greater than or equal to 0. So here the objective function is quadratic. Here it is, the power is 2, so it is quadratic, and constraints are linear. These constraints, these are the two constraints. Constraints are linear. So in our definition, it is mentioned that objective function is quadratic and all the constraints are linear. So we can write this as, another way of writing this one is minimum of f of x equal to x1 x2 into 3141 into x1 x2 plus minus 2 minus 3 of x1 x2, such that this is the matrix representation. Actually this one is x transpose, this is x transpose, x is this one, this matrix, column matrix x1 x2, so it will be x transpose, and this one is q, this is our q, and this is x, plus our coefficient matrix is, then next plus C transpose. C transpose is minus 2 minus 3 into x is x1 x2, such that these are the constraints. So how will you prove this one is a quadratic programming problem? Q equal to matrix 3 1 1 4. So first of all we can find the D1. This D represent determinant. So 3 is greater than 0. Also the next determinant is D2. D2 is 12 minus 1. 12 minus 1 is 11, which is again greater than 0. Therefore Q is positive semi-definite matrix. Solve the QPP problem using graphically. Minimum x1 minus x2 the whole square plus x2 minus 1 the whole square subject to x1 plus x2 less than or equal to 2. Also x1 x2 greater than or equal to 0. So once we plot this equation, x1 x2 is less than or equal to 2. So x1 x2 is, this line represent x1 plus x2 equal to 2. So our objective function is, this one is a circle. It is x square plus y square. It is a circle. So how will you find the slope? It is the center of this circle. Center of the circle is, this magenta point is our optimal point, that is x1 y1 is the optimal point. How will you find the optimal point? We know the center radius of this circle, that is x1 minus r the whole square plus x2 minus r the whole square. That is, we got 2, 1. This is our center point of this circle. The circle whose radius is larger than this is not optimal. So this point is 0, 2 and this point is 2, 0. And we got a circle here. If we plot a circle which is larger than this circle, then the radius will be like this. Radius is large, so it will fall on this feasible region. So feasible region of QPP is always a convex set because all the constraints are linear, so all constraints are convex function. Set constituting collection of convex function is a convex set. So we are having an equation x bar plus y bar. Okay, from this equation we can write it as x bar plus y bar equal to 2. Okay, again the slope of this one is y bar minus 1, that is this point. Slope of this point to this line. Y bar minus 1 divided by x2 minus 2. So we can write it as this slope is 1. That is, so we can cross multiply it. Y bar minus 1 equal to multiplying this one x bar minus 2. Again we can move this minus 1 to this side. So we will get x bar minus y bar equal to 1. So on solving this, we will get x bar equal to 3 by 2 and y bar equal to 1 by 2. This is the optimal point. So first point, feasible region of QPP is always a convex set since all the constraints are linear. Another point is, unlike linear programming problem, the optimal solution of QPP or NLPP may not attain at the vertex of the feasible region.